Hello to all of you and welcome back to my SP2 channel. This lecture is all about oxidation reduction reactions. We're going to start by kind of introduction. We have oxidation numbers, we should define them. We're going to be looking at the oxidation of metals by acids and salts. I also have the activity series for you, and then we have a practice at the end together. Okay, so starting by our introduction, we're going to be looking at the definition of oxidation and reduction. Okay, so for oxidation is the process where we have our substances losing electrons, resulting in an increase in the oxidation number of them. Okay, I want to talk about the oxidation number on the next slide. Okay, so for now, let's just say that if you have loss of electrons, we're going to have an increase in our oxidation number. On the other side, we have reduction, which is exactly the opposite process, right? In this process, the substance are going to gain electrons, resulting in a decrease in our oxidation number. Now, these things are very common, and they are happening around us a lot. A very good example is looking at the Statute of Liberty, right? As you can see, the green coding here is due to the formation of copper oxide, so the copper here is oxidizing. And the other example is rust, where we get it when we have the iron that undergoes corrosion, right? So oxidation of iron is pretty much known as rusting. Okay, now what do I mean by oxidation numbers? So before we identify an oxidation reduction reaction, we must have a kind of bookkeeping system, or let's say a way of keeping track of the electrons gained by a substance being reduced or electron lost by a substance being oxidized. Okay, the concept of oxidation numbers, which is also known as oxidation states, was devised as a way of doing this. So each atom in a neutral substance or an ion is assigned an oxidation number. Okay, so for example, if I have, let's say, a monoatomic ions, the oxidation number is the same as the charge of that, right? But if I have a neutral molecule or a polyatomic ions, their oxidation number of a given atom is a kind of hypothetical charge, right? That we have it based on the distributions of the electrons among those atoms, okay? So now, how we can keep track of that? There are going to be a bunch of rules here that I'm going to stay on this slide for a couple of minutes and review that together, okay? So starting by the first one. For the elemental form, for any atoms in their elemental form, the oxidation number must be 0. So for example, if I have hydrogen in a form of H2, right, which is my diatomic, then it must be 0. If I have phosphorus atom in a form of P4, that must be 0 as well, okay? The second one is for the monoatomic ions, okay? So the oxidation number must be equal to the ionic charge. For example, if you have potassium ion, then it's going to be just +1, right? Or if you have sulfide, then the oxidation number is going to be -2, okay? In our ionic compounds, if you see any of the group 1 metals, let's say sodium, then it's going to be always +1. If we have any of the group 2 metals, they're going to be +2. And if I have any of the aluminum group, right, which is group 13, they're going to have +3, okay? Now, a kind of side note here, when you try to write your oxidation number, we try to write the sign before the number to distinguish them from the actual electronic charges, right? So if you want to go by the charge, you would say 3+. But if you say +3, that means you're referring to the oxidation number, okay? Now, for our nonmetals, there are going to be a few of them that are quite common. So for example, if I have oxygen, that is usually -2, unless you have that in the form of peroxide, which is -1. For hydrogen case, it's typically +1 when it's bonded to a nonmetal, and it's going to be -1 when it's bonded to metals, okay? Fluorine is always going to be -1, okay? And if you have any other halogens, right, those are the ones that are also typically -1, okay? Unless you have them with oxygen, okay? And the last thing is, it's all about like the sum rules, which means that if you have a neutral compound, when you sum all of your oxidation numbers, that must be equal to 0. if you have any polyatomic ions, right, you can add all of your oxidation numbers, and that must be equal to the charge of that polyatomic ion, right? So this would be very helpful. You can use these rules, right? These are the ones that are kind of known. And for any of the compounds or any of the polyatomic ions, we can actually use these rules to solve them for the, unknown oxidation number. Okay. I hope that makes sense. Perfect. Now we're going to be looking at the oxidation of metals by acids and salt. So let's take a look at the oxidation numbers for this reaction. What I have on the reactant side is just magnesium, right, which is reacting with hydrochloric acid. It is producing magnesium chloride and hydrogen gas. Okay, so it seems that the oxidation number of magnesium is changing from 0 to +2, which is an increase, right, in the oxidation number, and it is indicative that the atom has lost electrons, right? So we can say magnesium has been oxidized. On the other side, when you're looking at the proton on hydrochloric acid, you start from +1 and then you go to 0, right, for hydrogen gas, which means that the ion here has gained electrons, right? And you can say this proton has been reduced, okay? Now, when you're looking at your chlorine, on the reactant side, we have -1. On the product side, we also have -1. So there's no change in the oxidation number of chlorine, right? And this is exactly what we have for the spectators, if you remember them, right? In our previous lectures, we talked about the spectators that are just there to balance out the charge, but they're not really directly involving any sort of chemical reactions, right? So I can cross out my chlorine, and that is going to give me my net ionic equation, the actual reaction between magnesium and proton, right? Okay, cool. Okay, so let's continue our discussion and let's take a look at the reaction between a metal and either an acid or a metal salt that is typically following this general pattern. So I have A plus BX that goes to AX plus B, and I can have my metal plus the acid that is producing salt plus the hydrogen gas. So for example, I have zinc reacting with hydrobromic acid, and it is producing zinc bromide and hydrogen gas. Or you may have metal A reacting with the salt of metal B that is actually producing the salt of metal A and kind of releasing metal B. For example, I have manganese here reacting with lead nitrate, and they are producing manganese nitrate, and I also have kind of releasing of this lead in a solid form. Okay, so in these reactions, the metal reacts with an acid to release hydrogen gas and form a salt. And what we see typically is a more reactive metal is displacing a less reactive metal from its salt solution. And guess what? We can call this reaction as displacement reactions, right? That is totally makes sense. So following our discussion, it's actually a very good question to ask. How do we know if any of this displacement reaction is going to happen or not? Okay, to answer this question, we need to look at our activity series. As you can see here, this table is actually very large. That's a very big series. I could not fit all of them here, so I only have some of these metals. Okay, and looking at this table, the activity series rank the metals based on their ability to lose electrons or to oxidize, right, and displace the other metals or hydrogen from their compounds. Okay, now any metal on the list can be oxidized by the ions of the metals below it. For example, when you're looking at copper and silver, so here is my copper above the silver, right? That means copper metal is oxidized by silver, right? And I can write the reaction as my copper that is giving away electrons to silver plus, and we're going to have copper 2 plus plus silver. So my copper here lost electrons, right? It got oxidized, and your silver plus gains electron and it got reduced. Okay. Now looking at the bottom of this table, you've got copper, silver, mercury, platinum, gold, which is my favorite metal. These are all pretty stabilized metals. It's not easy for them to let go of electrons, and that's why they are very expensive, right? Especially for the last two, these two are the most expensive metals on the earth. Okay, and as I told you, gold is my favorite metal. Okay, so that brings us to the practice. So here's the question. Will an aqueous solution of iron 2 chloride oxidize magnesium metal? If so, write the balanced molecular and net ionic equation for this reaction. Okay, so I want you guys to look at our activity series and see where we have magnesium and iron. So if magnesium is on top of iron, that means it is easier for magnesium to let go of the electrons, right? So yes, this reaction should happen. And in order to write the formula for the salt to produce, we can think about our common charges, right, that we have for our ions. So magnesium belongs to group 2. So the charge for that must be Mg2 plus, right? And then chloride is our halide, so it should have Cl with a negative charge, right? So your salt is going to be MgCl2, magnesium chloride. I can write out my balanced molecular equation as my Mg, magnesium, reacting with iron 2 chloride, and is producing magnesium chloride and iron. Okay, so this is going to be my molecular reaction. Now follow me on the next page for the net ionic equation. So I know that for both iron 2 chloride and magnesium chloride, I have soluble, strong electrolytes. So I can separate their cations and anions. I also know that our spectator ion here is going to be our chloride. So we can separate the ions. It's going to be Mg plus iron 2 plus 2 chloride. That goes to Mg2 plus 2 chloride plus iron. And then you can cross out your spectators, right? And we're going to get to our net ionic equation, which is Mg plus iron 2, and that goes to Mg2 plus iron. Okay, I know it was a really, really long one. We did it. We did it together. Thank you for bearing with me. It means a lot to me when I have all of you with me for the whole time, even for something like this, which I know it was a kind of heavy discussion. A very big thank you to all of you for watching this video. If you find this video helpful, don't forget to give it a thumbs up, and you can share that with your friends. If you're still enjoying the content and you still want to learn with me, you can definitely go ahead and hit the subscribe button. You can turn on your notification bell so you're not going to miss out any of our future videos. I told you before, I love to hear from you guys. Let me know in the comment below if there's any, questions or concern. I'm going to read them always by my heart. I promise that. Okay? Take care of yourself, and I'm going to see you soon on the next video. Bye-bye for now.